Hi, hello. So what we discussed in previous video is the concentration and concentration terms. Today let us take some numericals which may be asked on the concentration terms. So the numerical is calculate molarity, mass percentage, mass fraction and mole fraction of Ki if density of 20% W by W aqueous Ki is 1.202 gram per ml. So this is what the numerical is, and almost all the concentration terms you have been asked. Okay. So whenever you solve a numerical, what you should do is you first write the given terms or the given amounts. Which is given here, we have been given 20% W by W. See, the percentage composition is given. It means we can take the amount of solution as 100 parts by mass. Whether we are taking 100 gram or kilogram, that depends upon us. So here what we will do is, we will take 100 gram of Ki solution. If we are taking 100 gram of Ki solution, then according to this statement, the amount of Ki will be 20 gram. The amount of Ki will be 20 gram. So that is Wb. Of course, Wb is equal to 20 gram. You have been given. Then what will be the Wa? Wa will be 80 gram. Am I right? W by W. Okay. So then what is given? The density D. D is equal to what? 1.202 gram ml inverse. Am I right? So this is what has been given to us. Now let us see the molality. Molality, we know that what is the molality of a solution is, we have Wb upon Mb into, we are taking 1000 here because the amount is given in gram. Okay. So We. This is what the formula by which we can calculate molality. Am I right? Put the values. Wb is given 20 Mb, the molar mass of Ki. The molar mass of Ki we can calculate. Generally it is given, but here it is not given, so you can calculate. For potassium it is 40, for iodine it is 127, so it will be 167. Okay, the Mb, the molar mass of Ki is 167 into 1000 upon Wa. Wa is 80 gram. How much it is? 80 gram. So all the values we have put here, and the answer will be 1.5 mole kg inverse. This is what the unit of molality. Am I right? So this is how we can calculate molality. Easy. Next one is molarity, and molarity we know that the formula of molarity is equal to Wb upon again Mb into 1000 upon V, and this V in ml. So V has not been given. Am I right? But for our convenience, the density is given, and we know that density is equal to mass by volume. So volume will be mass by density. You can calculate here. So what we have is, volume of solution will be equal to mass of solution. How much? 100 gram. Mass of solution, because the density is given for solution. So mass of solution will be 100 gram. Density is given 1.202 gram ml inverse. Gram to gram cancel, we will have ml. It will go up. You know? So this is what we have, the volume of solution. So now we can put the values, that is Wb 20 upon 167 into again 1000 upon this 100 will come here, and 1.202 will go at numerator. Am I right? And the answer will be 1.45 mole liter inverse. See the units. Okay. here. So So we can see that at the same temperature the molality 1.5 but the molarity 1.45. It means the molarity is less than molality. Yesterday we discussed in the previous video that molality depends upon temperature, nature of solvent, nature of solute. It may be less than molarity, it may be higher than molarity, it may be equal to molarity. Okay, all three conditions may be there at constant temperature and pressure for a particular solution. So this is how we can calculate molarity. Next one is mass percentage. See, mass percentage. This is common sense. Already given 20% W by W. So no need to even calculate. This is already given mass percentage because mass percentage 20% Ki. Okay, so 20% Ki means this is the mass percentage. Next one is mass fraction. Okay, so mass fraction means the mass of solute by mass of a solution. Okay, mass of solute by mass of a solution, and mass of Ki upon mass of a solution, and that is 20 by 100. Mass fraction. So mass fraction, how much it will be? 20 by 100 is equal to 20 means mass of solute, 100 mass of a solution. Solvent plus a solute will be equal to 1 by 5. 5 to the 10.2. How much it will come? 0.2. Okay, so this is mass fraction. Then automatically the mass fraction of a solvent means water will be equal to 0.8 because the sum will be always 1 for mass fraction or mole fraction or whatever fraction. So this is how you can calculate mass fraction, and next one is mole fraction. Now we have to calculate mole fraction. So how to calculate mole fraction? We have not been given moles here. So what we have to do is we have to calculate mole. Am I right? So how to calculate moles? Because we have been given weight in grams. So if you are having weight in grams, by using mole concept you can calculate easily number of moles, and if you will have number of moles then you can easily calculate mass fraction. Am I right? So this is how we can calculate a mole fraction. Okay, because mole fraction is equal to number of moles of solute divided by total number of moles of a solute and solvent. Am I right? So this is how you can calculate a mole fraction. Let us see how it will come and what it will come, how much it will come. So mole fraction. Okay, so mole fraction means X Ki. Okay, instead of B we should write Ki because it is asked for. Ki is equal to number of moles of Ki upon number of moles of Ki plus number of moles of H2, and number of moles of Ki will be equal to 20 gram of Ki we are having. Molar mass is 167 divided by, okay, again 20 by 167 plus 80 by 18. Molar mass of water is 18, amount of water is 80 gram. So this is how you have all the values. Now you can calculate, okay, and it will come 0.0263. 0.0263. You can check it whether it is correct or not. Okay, so it is written here, so I have written here as well. So this is how you can calculate mole fraction of Ki. Likewise, mole fraction of water will be, you just subtract it from 1 because the sum will be 1. So you will get mole fraction of water. So this is how in the same molecule, same numerical we have calculated almost all the concentration term. Okay. Now next point what we are going to discuss here is the solubility. Okay. So what do you mean by solubility? First of all we will discuss that, and for that let us take a very general example. Okay, you might have seen water. Have you seen water? Yes. Okay, have you seen table salt, NaCl? Yes. So let us take a definite amount of water. Okay, and at room temperature, means temperature and pressure are constant. So let us start dissolving NaCl into that definite amount of water. Slowly we add NaCl, add NaCl, add NaCl, and a stage will reach where no more NaCl can be dissolved in that amount of water. Okay, it means what? It has reached at a maximum level. Now at this stage the solution is called a saturated solution. What is called? Saturated solutions. So what we can say is the amount of solute or a substance which can be dissolved in a particular amount of solvent at a constant constant temperature and pressure is called its solubility. What did I say? The maximum amount. Which amount? The maximum amount of solute or a substance which can be dissolved in a definite amount of solvent at constant temperature and pressure is called its solubility. Okay, or what we can say is the concentration of a saturated solution. The concentration of a saturated solution. Saturated solution means the maximum amount is already dissolved. It means the maximum amount is there for solute, and that is what is called its solubility. So maximum the concentration of a saturated solution is called its solubility. Is it clear? Yes. So now let us see the solubility of solid in liquid. See, we will discuss solubility of solid in liquid, solubility of gas in liquid, and solubility of liquid in liquid. These three types of solution we will be discussing in this chapter. Okay. So first let us take solubility of solid in liquid. Like just now we have dissolved NaCl, that is a solid, water, this is a liquid. So how this solubility depends on different factors. Okay. So for that what we say is if the interaction intermolecular action or interionic actions of particles of solute is similar to the intermolecular interaction of solvent. Okay, it means what? If we are taking a polar solute, say like NaCl, it is very polar, it is an ionic compound, it means it's a polar compound. Okay, so if we are dissolving a polar solute into a polar solvent, say H2O, H2O is a polar solvent, so it will dissolve. Okay, why? Because the interaction of NaCl are polar, interaction of water molecule are also polar, so both the interactions are same, and that is why they are dissolved. The NaCl is dissolved in water, and what is said is like dissolves like dissolves like in which reference? In polarity. In case of polarity we are seeing whether both are like or different. Okay, if the polarity is same, they are like solute and solvent. If we want to dissolve like benzene or anthracene into water, it will not dissolve. Why? Because benzene and anthracenes are non-polar compounds. Okay, so they will not dissolve in water. But if you will dissolve benzene or anthracene into like say chloroform or some other non-polar solvent, they dissolve into each other. Okay, why? Because what the principle says, like dissolves like. Is it clear? One term is there that is called dissolution. What is that? Dissolution. Dissolution means the process of solvation of a solute in a particular solvent is called dissolution. Okay, another term is used in case of dissolution, that is crystallization. Okay, crystallization means what? If there is a single, say a single molecule or a single particle of solute that is not dissolved, okay, that is not dissolved, then what will happen is, if a dissolved particle will collide with that solid particle, it will also try to come out of that solution. So what is said is, if a dissolved solute particle collide with a solid particle within that solution, then that solute particles which was dissolved try to come out of that solution. So this process of coming out of the solute particle out of solution, that is called crystallization. Okay, so what happens here is, in a saturated solution, what we do is, we take a solvent and start dissolving a solute into it. What will happen? The stage will reach where the solution become saturated. Okay, and in that case, this is the solvation and this is crystallization. So at this stage, okay, the process of solution or solvation, okay, the process of solvation and crystallization are in a dynamic equilibrium. Means the solute particles which are going into solution by the process of dissolution, at the same time the solute particles is coming out of that solution due to crystallization. It means the rate of solvation will be exactly equal to the rate of crystallization for a saturated solution. Now if we are making any change at this dynamic equilibrium, this is what is called the dynamic equilibrium is stabilized in a saturated solution. If now any change is happening at this stage, then the dynamic equilibrium will shift in such a direction that the made change is diminished, and this is what is called the Lee-Catelier principle, and this is happening at constant temperature and pressure. Say what we are doing here is, suppose we are leaving this solution open. Okay, so what will happen? Some of solvent particles will evaporize. It means the amount of solvent will decrease, and in that case the dynamic equilibrium shift in backward direction. So what will happen? The crystallization happened. Crystallization. Okay, so and this is what? Solvation or dissolution. Okay, so if any change is made, then the equilibrium will shift according to Lee-Catelier's principle. Okay, so this is what is called the dissolution and crystallization. Dissolution means the process of solvation of particles into that solvent. Crystallization means if the soluble particles are colliding with solid particles, then it will come out of that solution, and that is called crystallization. And in a saturated solution, there is always a dynamic equilibrium between these two processes. Am I right? So this is how we can discuss the solubility. Now let us see the effect of temperature and pressure. Temperature and pressure, here principally we will discuss the effect of temperature, because the process of dissolution may be of two types. One is exothermic and another one is endothermic. Okay, if the process is already exothermic, it means what? The enthalpy of solvation, the enthalpy of a solvation is less than 0. It means the process of dissolution is an exothermic process, and in that case if we are increasing temperature, it will have an opposite effect. It means the solubility will decrease. The solubility will decrease on increasing T. The solubility will decrease for an exothermic dissolution. If the dissolution or solvation is an endothermic process, it means delta S solvation is greater than 0, it will be an endothermic process. Generally what we see is this is what happens. Okay, so the solubility on increasing temperature, the solubility will also increase. If solubility will also increase in case of endothermic process. So this is how we can see the effect of temperature on solubility. Okay, if we see the effect of pressure on solubility, then the liquid solutions are almost unaffected by the effect of pressure. Why? Because liquids and solid stages are incompressible. Okay, means we cannot compress a solid or a liquid by applying pressure on it. Okay, so if we are unable to pressurize a solution, then of course the effect will be negligible. So what is said is the liquid solutions are unaffected by pressure. Liquid solutions means if a solid is dissolved in a liquid, because both are unaffected by pressure, and hence if we are changing pressure, there will not be any considerable effect on its solubility. But in case of gas in liquid, there will be a considerable effect. Okay, so we will see that effect in our next video, where we will be discussing the solubility of gas in liquid, and we will discuss Henry's law there. So for the day, I think it is sufficient. Thank you very much for watching. Keep on studying. Happy chemistry.